So thanks, Marcel, for the invitation. Yes, the keyword here is again. Last year, we had a great idea. Okay, we're going to do NLP for the enterprise. And we had a plan. And then, well, reality. We had to change the plan during this year because of some facts that we were not aware of. And I want to go deeper into some problems that we faced and the solutions that we found. So a bit of context, Swisscom is best known for being a phone operator. And if you look at the name, well, it's Swiss, and then it's com, hence we're selling phones. And people have been used to communication as a means of communicating to another human. But that is changing, especially in the enterprise context. You need to communicate to robots increasingly. And this is not new. We've been doing this for a while. We've been communicating to machines. We've been telling them what to do. What changes now with AI is who actually needs to do the job, who needs to reach out and help the other party understand what's going on. And for the first time, we can have a useful AI that will help us in communicating. In order to have a useful communication with the bot, we need to combine a lot of narrow pieces that we build separately and have a cycle. So we need to give the user value at the end of this communication loop. So first, we need to normalize, and this usually means understanding speech. Then we need to understand what the most important parts of what's being said are: emotions, sentiment, key phrases, entities, and then do something with those. And this is very app-specific. It can be recommendation, it can be summarization. It really depends on the client. And then you have to give the user something back. It can be a dialogue, or it can be just a form of insight, an aggregation. Machines are way better at aggregating than we are. So this is more or less where we were last year. Grand vision, okay, we're going to work on all of these and then deliver value at the end. But little did we know that all of the algorithms that we were actually hoping to just put in production relied on the assumption that we have the data. Well, we don't. And you go to a client, and it's very rare that they have any data to work with. And this hurt us the most in language understanding. And I'm going to go deeper into 3 use cases where data constraints led to new solutions. When you talk about bots, most people think of goal-oriented bots. You have a bot, you tell it to do something. For instance, list some classic gangster movies. Okay, don't judge. Here, the bot needs to understand that the slot it needs to fill is the genre of the movie. And the value for that slot is gangster. And if you have a lot of data, thousands of samples, this is an easy job. Okay, this is classic sequence tagging. Given data, you're fine. But if you only have 10 or 20 or 50 data points to work with, it becomes a very hard problem. So then the question is, how do you pick the right sentences to label or the right utterances to label, given that you have a lot of unlabeled ones? The intuition would be that if you have these 6 sentences, I would rather have one of them instead of more, because if I already have the first one labeled, the value that I get from the second and third decreases rapidly. Luckily for us, we can actually figure out that these are similar. We used a sentence embedding scheme that was actually created by Martin. Thank you. And with that, we noticed that all of these sentences are actually in the same region of the space, right there. Of course, this is projected, so it doesn't look really like that, but close enough. So then, if you know that all of the ones that you don't want are in that very tight space, the problem becomes, how do you pick the ones that you do want? So how do you create a scheme or a ranking that will give you points spread out in this space that will cover all the dense regions, yet be far away from each other? And Mladen, who's a student with us now, came up with a submodularity-inspired function that penalizes each new data point by the closeness to the other members of X, which are the previously chosen data points. Doing this, it's easier to focus on the right data. And it beats active learning. This was the surprising finding that we had. We had various active learning functions to benchmark against, and this was better. All right. Second case. If you have one client that comes to you with a document and just wants the key phrases out of that single document, you have nothing else to work with, just the assumption that, well, language doesn't change. Then what we do is, again, use that same space and embed the document. And once we embed the document, we take all of the candidate phrases, which are a lot, based on syntactic rules. You take the noun phrases, for instance, or larger constructs based on nouns. And you could stop right there. You could give the client this whole mess as a result. But this information overload leads to, well, an unhappy client. So the question then is, how do you select the best candidates? How do you pick those blue points? And this is a method that another student has created, and we called it Embed rank, because we rank based on embedding distances. And actually, I forgot to say, all of the work that I'm going to present today is already available on archive. So just look at the title. So just as in the previous case, the distances in the embedding space give us enough information to discriminate useful candidates from less useful ones. And even more, to have a nicer look here, you can cluster them. And you can say, given the amount of information that the client actually wants at the end, I'm just going to show them additional social assistance benefits and not employment support allowance. Note that, okay, the wording is not the same, but the meaning is. So the fact that we clustered them is added value for the customer. A third case departs from this direct use of the embedding distances. And it's sort of a transfer learning. We already knew how to extract quality phrases. And we want to transfer that ability to finding good targets of opinions. Because, again, if you have a good data set, finding the targets of opinions is pretty simple. But if you're in a new domain, getting that data, as Olga mentioned, is pretty hard. So the system was also created during a master thesis. If you see a pattern by now, there is one. You take the phrases that you get, this works. Take some phrases that you get from sentences of reviews, you figure out which are the quality phrases within, just prune out the ones that don't make sense, and then with some syntactic rules paired with a sentiment lexicon, figure out which are the phrases that are attached to words that normally bear some polarity. And this becomes a very noisy data set, but it turns out it's good enough. Because this noisy data set will have a pretty high precision and an extremely low recall, 20% or less. But if you create a model using this noisy data set, a lot of the noise dies down, and a lot of the features which were hidden give you an extra value, and you can double or triple the F-score. Data constraints are not a problem just for language understanding. If we're talking about how to structure dialogue, it's even worse. Because very rarely do people actually have any sort of data of interactions with bots before they deploy a bot. So you have to make it up, and all that is costly. But if you already do it for one domain, for instance, you do it for movie booking, couldn't you just use some of that knowledge for a second domain, for a second client? And these two domains, they seem to be very, very different. However, they do share some of the slots that the bot needs to understand. Bots. You still talk about cities, dates, and number of people in both cases. So the trick would be to use some of the data, some of the knowledge from the first domain and apply it in the second. And I'm not going to go deep into how transfer learning works, but in essence, you learn some weights, and then you keep them for the target domain. We were surprised by the results. The success rate of the bot is consistently even 50% higher in relative terms if you use the transfer than if you don't. It's not just that you learn more quickly because you have a better starting point. The final result is consistently better. So we had the assumption that transfer learning is going to work in terms of speed. We just didn't know that even if you plug in all the data from the target domain, you still have a better result. This is done by a fourth master student. All right. Data constraints are bad, but they're not everything that we work on. So we also want to have better algorithms to serve to our clients. And better algorithms, if you're talking about app-specific computation, that's hard to do because you don't know what you're actually improving. But we do know that they come from the same family of functions. So if we're talking only about neural models, then there's a high likelihood that generating better architectures, period, will help with what we're doing. And you've heard this before this morning. Neuroevolution is now a thing. It's important to be able to evolve architectures in the absence of a data scientist. We just don't have the resources to do it yet. We can't go to a client and ask them to pay just 10,000 times more and they'll get something better. It's not feasible right now. So our work in AutoML revolves around driving the cost down. One way to do this is to actually turn this problem, which was usually a reinforcement problem or a GA problem, into a supervised learning one. How could you create or evolve better architectures in a shorter time if you have bigger blocks to work with? Instead of making individual changes, add a multiplication here, add an addition there, can't we just add full LSTMs? The problem would be knowing that an LSTM is good for this situation. And to get this knowledge, we looked at all the architectures that are freely available on GitHub. And you can use GitHub as a source of reusable models, of modules. This is a longer discussion, and I really believe AutoML is in its infancy, and that this is the way forward. Okay, final thought. We had a problem with the client who wanted a summarizer. And this is a form of insight. Okay, they had a big text and they wanted a small text with the same meaning. And it's all fine if you're talking about an extractive summary. Okay, so if you take this text here, which comes from a known data set, and you just want to extract the most important sentence, that's not hard. You can rank the sentences using whatever scheme. But if you want to create an abstract summary, you need to generate new text. And the business people were in awe. What do you mean the machine wrote text, like new text? And we were very convinced that that was the case. And then we saw that the results looked eerily similar to the original text. So much so that they were actually copied word for word from the original text. And we were calling this an abstractive summary. And this is actually the state of the art. This was published last year, and this PGNet is an extremely powerful model that fails in being abstractive. And the solution that we found, and this is not even on archive yet, hopefully this afternoon, is to add a diverse beam search to the mix. This is a method coming from Vision that generates new captions for a given image. But for us, it's a way of creating better summaries by making them less abstractive. And not only does this come at little cost to the actual Rouge score, it improves the Rouge score. So, going back to the usefulness, the fifth element that I've shown was created by a fifth master student. Given the constraints we have on the resources we can allocate to research, we work a lot with students. So if you're a master student and if you're preparing for finding a project for next year, these are the kind of things we do here, and we're at EPFL. If you want to know more, for instance, about the things that I have not mentioned, for instance, speech recognition and Swiss German, this was the highlight of last year, I invite you to the tables we have outside.